Welcome. In this video, I'll be talking about hypothesis test for a population proportion. And so I'm going to actually just start in with an example. And then as I work through the strategy, I'll kind of just point out the different pieces here. So the first step for conducting a hypothesis test is to state the null and alternative hypothesis. So I want to make a statement about H0 and H1. So this is a test about a proportion. So these are both going to be statements about P, the population proportion. The null hypothesis is going to be a statement that P equals a certain value, and the alternative hypothesis is going to be a different statement, either that this is less than that amount, different from that amount, or greater than that amount. So again, I'm just going to make up a number here, and let's say that you want the assumption is that in a certain population, the proportion with a certain characteristic is 0.75. And as a researcher, you wonder if maybe this needs to be updated, and if in fact it is more than 0.75. So you're setting up a right tail test for the population proportion. And all right, so we know what we're testing here, and we're going to go and gather some sample data. And so we maybe are going to find, 500 people, and to see if they have this characteristics. And maybe, let's say 400 do. And so from this we can calculate our sample proportion. So P hat, that's X over N. In this case, that's 400 out of 500, which is 0.80. Now, certainly in this one sample, we did get a result that was more than what we assumed to be the population proportion. But keep in mind, we expect variety from one sample to the next. So in order to conduct this test, I need to say, I know that this is different, but is it different enough to be evidence that would give me a reason to dispute this assumption, this claim that the proportion is 0.75? So in order to understand the mechanics of the test, we need to think about the distribution of P hat. So if certain conditions are met, I know that the the sample proportion has a normal distribution, and it is centered with the population proportion. So remember, I'm giving this the benefit of the doubt. This is the assumed truth here, the null hypothesis. So it should be centered at 0.75. And the standard deviation is the square root of 0.75, that's P, times 1 minus P, so that would be 0.25, all over N. In this case, that's 500. Now, I'm going to simplify this. Let me just grab my calculator. And I take, let's see, 0.75 times 0.25 and divide by 500, and then take the square root of that. I get that this is approximately 0.02, about 2%. So this would have a bell-shaped distribution centered at 0.75. And if I go 1, 2, 3 standard deviations in either direction, each one of those standard deviations is 2 percentage points. So this would be 0.77, 0.79, and 0.81. This would be 0.73, 0.71, and 0.69. So the result that I got in my sample, so remember, this was what I'm calling my evidence. I took a sample and I got a result of 0.8. So 0.8 is somewhere over here. Now, what I'm wondering is if this is an unusual result. So when I constructed this bell-shaped curve, I'm assuming that the center is at 0.75 because that was the value in the null hypothesis. And remember, this is what I'm assuming to be true. And so I've constructed my whole picture around that assumption that that's where the center is. And then I went out and collected my sample data, and I got this result of 0.8. Now, is that something that I would anticipate if this is true, or would this be surprising when this is true? Well, if I had a result that was much closer to 0.75, I would probably just give up and say, I don't have any evidence to dispute this. But because I'm getting a result that's over here in the right tail, and notice I was conducting a right-tailed test, because I have a result that's over here in the tail where things are less likely or more unusual, it gives me a reason to think, maybe the population proportion is not 0.75, and maybe in fact it is greater than 0.75. So the way I'm going to look at this is I'm going to find the area that's in the right tail, and that's because this is a right-tailed test, and think about how likely is it that I would get a result of 0.8 or more if the true population proportion is 0.75. So that's what I want to do in finding this area. So I'm going to use my distribution menu and look at the normal CDF. I'm going to find the area that's in this tail. Now remember that this goes on to infinity. So I want to take a normal CDF, and the lower bound I'm going to use 0.8, and the upper bound I'm going to just use a really big number, 10 to the 99th. And the assumed center of distribution is 0.75, and the standard deviation, in this case, the standard deviation in the sampling distribution is 0.02, and let's just see what we get. So this probability, or area, is 0.006. So, actually 0.06. And the point is that this is a small area. It means that getting this result of 0.8 or anything, any similar results, anything bigger, the chance of that happening when in fact the proportion is 0.75 is just 0.006, less than 1%. This seems like a really unlikely result, the result that I got from my sample, if this is true. And in fact, it's so unlikely that I am actually going to dispute, bring issue with this statement that the proportion is 0.75. Now, the tricky part about hypothesis testing is how are we going to define unusual enough to dispute this claim? Well, that's where we use a level of significance. The level of significance, which we use the symbol alpha, this is the chance of a type 1 error, and that's rejecting the null hypothesis when it's true. So this standard that we set for alpha is what we're going to compare this area in a tail to. Usually we want to limit the chance of a type 1 error, and we'll pick values like maybe 5% for alpha, or in some cases you may pick 1%. If you have if the consequences of making a type 1 error are not too dire, you may even have a level of significance as high as 10%. But now notice in this case, whichever of these I would select, 10%, 5%, or 1%, this probability is less. And so it is going to meet my standard for unusual. So I'll call this your standard for unusual. And so as long as I meet the standard for unusual, then that's going to say, you know what, I don't buy this. I'm going to reject. So when you're, by the way, I should go ahead and introduce the term. This probability that we find in the tail is called the p-value. And if your p-value is less than alpha, you will reject the null hypothesis. if your p-value is greater than alpha, then you fail to reject the null hypothesis. So those are our only two options as far as for the decision of the test. So before you start a hypothesis test, you should pick a level of significance. You'll usually do this based on, like I said, the consequences. How dire is it if you make a type 1 error? Meaning, by dire, usually that means that it would be an expensive mistake, costly maybe in terms of lives lost or money lost. But if the consequences are high, then you would want to choose to diminish the chance of that type 1 error, and so you would choose a stricter test, meaning with alpha of 1%. This is stricter than alpha of 5%, which is in turn stricter than alpha of 10%. So, all right, the other thing I want to mention is if we were conducting a left-tailed test, I would be looking in the left tail for the probability. If you are conducting a two-tailed test, then you can find the area in the closest tail, but we have to double this value to get the p-value. So I'm going to stop there with this like an overview of hypothesis tests, and then in the next video I'll show you some examples with some applications about how this all works, and also how to do some of this in your calculator.